Colleagues, good morning, learners, especially our grade 12 learners. You are almost there. It's the last part of your journey for school physical sciences, and hopefully many of you will take it up at tertiary studies. But we're here this morning to do our session on the photoelectric effect. So, colleagues and learners, let's get straight into it. Okay, we're dealing with optical phenomena this morning and specifically the photoelectric effect, as I've mentioned. Here are our examination guidelines with regards to this specific topic. I'm going to go through this point by point. It says, describe the photoelectric effect as a process whereby electrons are ejected from a metal surface when light of suitable frequency is incident on that surface. I've got a simulation that I'll show you shortly that specifically points out what is meant by each of these points. Right. Secondly, state the significance of the photoelectric effect. Third bullet point, define threshold frequency as the minimum frequency of light needed to emit electrons from a certain metal surface. You'll see that the symbol for threshold frequency is F with a subscript 0. Then our next bullet point, define work function as the minimum energy that an electron in the metal needs to be emitted from the surface, from the metal surface. And again, the symbol for work function is the W with a subscript 0. And then perform calculations using the photoelectric equation. And this equation can be given as E, which is the energy of the photon is equal to work function plus the maximum kinetic energy, where E, energy of the photon, is equal to HF. You'll remember this equation over here from your work in grade 10 when we discuss the electromagnetic radiation. And work function is equal to Planck's constant, which is h, multiplied by the threshold frequency f, and the kinetic energy, or EK max, of an electron as it is emitted from the surface of a metal is equal to half mv squared, which is your normal equation for kinetic energy. But all of these equations and all of these points that I'm mentioning now, we're going to get into a little bit more detail as we work through this topic. And the next one, explain the effect of intensity and frequency on the photoelectric effect. This I will simulate to you using a PhET simulation shortly. And then lastly, state that the photoelectric effect demonstrates the particle nature of light. Now, we will have a bit of time this morning. So before I go on to our next slide, there's just a couple of things I want to call to your memory again. And let's actually start with the last point first. When we've discussed now studies of light, the nature of light, what often pops up is the dual nature of light. So light is a wave. It's a transverse wave, but light also has a particle nature. So light is both a wave and a particle at the same time. Now, remember when we did the electromagnetic spectrum in grade 10, we discussed the wave nature of light. And so light falls into the visible spectrum, is part of the electromagnetic spectrum, or visible light forms part of the electromagnetic spectrum, and it is a transverse wave, and we discussed that property of light. But we also need to consider the particle nature of light. Now, not only the wave nature of light. And let's move on to our next slide. Okay, so we'll be dealing with what you also need to understand is your emission and absorption spectra. Now, these can be demonstrated, and many teachers demonstrate these spectra during practical investigations, but I'm going to go through the theory part of it mainly today. So, next bullet point, explain the formation of atomic spectra by referring to energy transition. And then explain the difference between atomic absorption and emission spectra. Now, on the right of the slide, you can see these line spectra indicated in this area over here and this area over here. The first one, A, is an emission spectrum, and the second one, B, is an absorption spectrum. And I will explain what the meaning of each of these is. Right, so let's look at an atomic absorption spectrum, which is the second one, which is B over here. So as I go through reading this, you can have a look at this image on the right. This is the one labeled as B. It says an atomic absorption spectrum is formed when certain frequencies of electromagnetic radiation passing through a substance is absorbed. Right. Now, the area where you have absorption, those areas are indicated by black lines against a continuous spectrum. Now, remember, the spectrum of white light is a continuous spectrum from red right up into violet. So remember the 7 colors? It's red, orange, yellow, and you can see it in the background over here. Red, orange, yellow, green, blue, indigo, and violet. And so your absorption spectrum gives black lines against a continuous spectrum. I'm going to give you, let's read through the rest of this definition. For example, when light passes through a cold gas, atoms in the gas absorb characteristic frequencies of light, and the spectrum observed is a continuous spectrum with dark lines where characteristic frequencies of light were removed. The frequencies of the absorption lines are unique to the type of atoms in the gas. Right. So I don't want to dwell too much on this, but this is a very clever tool that physicists use to identify specific types of gases. So, neon gas, helium gas, oxygen gas, each one of these gases will have a typical fingerprint. They will have a typical pattern of these black lines against a continuous spectrum where frequencies from the visible spectrum is absorbed. It's a quite technical and complicated thing to get your head around. It will be enough for you to know these definitions, but what I'm trying to do is also explain how these things come about. Right, so the second image, the B image over here, this is our absorption spectrum, and the definition in this first bullet point goes with this image here. Right, let's go on to the next one. An atomic emission spectrum is formed when certain frequencies of electromagnetic radiation are emitted due to an atom making a transition from a higher energy state to a lower energy state. And then the example, atoms in a hot gas emit light at characteristic frequencies. The spectrum observed is a line spectrum with only a few colored lines. Let me just take this out of the way so that you can see. A few colored lines of frequencies unique to the type of atom that is producing the emission lines. So now we are talking about image A in this diagram on the side. The difference between my emission spectrum and my absorption spectrum is, in my emission spectrum, I have a dark background with colored light or lines of specific colors against the dark background. Now, remember from grade 10 that the color of light is related to the frequency of light. And if the color of light is related to the frequency of light, it is then also directly related to the wavelength of light. Because remember your equation for the speed of light is equal to frequency times wavelength. So since c, which is the speed of light, is a constant, which is 3 times in a vacuum, 3 times 10 to the power 18 meters per second, it means that any change in frequency will have a specific change in wavelength associated with it. Remember, because the speed of light is a constant. So we can confidently say, if we know what the wavelength of a specific type of light is, we also know what the frequency of that light is, and we also know what the color of that light is. And this is one of the very amazing things about physics for me, is that you can relate a specific color of light or range of colors to a specific frequency or range of frequencies. So when we look at an emission spectrum, I'm going to go through it again. For example, atoms in a hot gas emit light at characteristic frequencies. Remember, when it emits light, when the atoms in a gas emit the light at specific frequencies, we are going to see specific colors. The spectrum observed is a line spectrum with only a few colored lines of unique frequencies, frequencies unique to the type of atom that is producing the emission lines. Right, let's go on to our next slide. Right, so for our pretest, before we do our pretest, apologies. I just want to show you something that I have on my computer over here. Right, this is related to some of those points that I mentioned in our examination guidelines, and I just want to show you the simulation before you get to the pretest. Again, I'm going to go back to our previous slide. So first bullet point, describe the photoelectric effect as the process whereby electrons are ejected from a metal surface when light of a suitable frequency is incident on that surface. So what did I remind us of this morning? That light of a certain frequency is also light of a certain color, is also light of a certain wavelength. So when you talk back to yourself about this content, you can say it in the same manner. Light of a certain frequency is light of a certain color, and that is how we see frequency. Our brain registers frequency, different frequencies of light as different colors. And so when light of different frequencies are incident, when we shine it onto the surface of a metal, electrons will be kicked out of the surface or ejected from the surface of a metal. Here's a nice little diagram in the corner, in the right-hand corner over here. Then also state the significance of the photoelectric effect. We'll get into that a little bit later. Threshold frequency, etc., etc. And the last bullet, the second last bullet point also says explain the effect of intensity and frequency on the photoelectric effect. And we are actually going to, I'll demonstrate that as well. So just to put it into perspective again, the first bullet point, describe the photoelectric effect as a process whereby electrons are ejected from a metal surface when light of suitable frequency is incident on that surface. I'll demonstrate that bullet point, first bullet point. And the second last bullet point, which says, explain the effect of intensity and frequency on the photoelectric effect. So I'm going to demonstrate that again. And for many of you, this will just be a reminder, but it is a good reminder of all of the various aspects that we're dealing with when we look at the photoelectric effect. So let's go to our simulation. Right. So there's a slide control over here. And this slide control, okay, maybe before I start. So this electrode over here is covered with a specific metal. And the metal in this case is sodium. So you can see there's another drop-down menu over here. There's a drop-down menu over here. And in this drop-down menu, I can change the type of metal. So from sodium, I can turn it to zinc, and you can see the color kind of changes there. From zinc, I can change it to copper, and the color goes a more orangey color. From copper, I can change it to platinum, and so on and so on. So let's go back to sodium. So this electrode is covered with a metal. And then we have a source of light over here. And this source of light is linked. At the moment, it is linked to various wavelengths. So the purple, you can see where the bulb is supposed to be. You can see there's a purple color over here. That purple color corresponds to the purple on our continuous spectrum that is given at the bottom over here. Now, remember, we have a spectrum of white light that goes from red, of visible light, that goes from red to violet. This spectrum, however, over here, I have ultraviolet right on the side, and I've got infrared right on the other side. Now, just a quick little tip. And Mr. Mentor, you can just keep an eye on the clock for me as well with this. But I will try and fill in for many of our learners just some of the context of a lot of what we'll be discussing this morning, and that will take us a little bit away from some of the key points, but it's absolutely vital to fill in all the gaps. So let me quickly go. So again, in grade 10, we know that infrared basically means beyond, just before red on our EM spectrum, on our electromagnetic spectrum. So just before red, you get infrared, and then you get your visible spectrum. So that is indicated on reverse in the way that we normally observe it. So we're starting, if this is infrared, the first color will be red, and then it will be orange, yellow, green, blue, indigo, and violet. And then the term ultraviolet means beyond violet. So beyond violet, you have your UV or ultraviolet. On the side on the right, before your red, you get your infrared. Right, now, this here is a scale of light on the EM spectrum, on the electromagnetic spectrum of different wavelengths. Now, remember what I said earlier. If you know what the wavelength of light is, you immediately know what the frequency of that same light is. Why? Because of the wave equation for light. C, which is the speed of light, is equal to frequency. Sorry, I've lost my pen this morning, and I feel like a gunslinger without a gun. But anyway, I'll continue. C, which is the speed of light, is equal to frequency multiplied by wavelength. So if we know what the wavelength is, we also know what the frequency is. So what I'm effectively doing is, as I'm changing the wavelengths on the sliding scale, I am changing the frequencies as well. And especially in my visible spectrum range, which is from red to violet, as I change the wavelength, I change the frequency. As I change the frequency, I change the color. And have a look at those beautiful color changes on my bulb over here. See my light over there? As I change my wavelength from red to orange, I change my frequencies. As I change my frequencies, I change my color. Right, so okay, so we have that. So that is the sliding scale for the various frequencies that corresponds to the different colors of light. This slide scale over here, this slide scale shows the different intensities, and the intensities, you can see as I change the intensities, basically maybe it will work better for a different color. So as I change just ignore the electrons at the moment. As I change the intensities, I want you to have a look at how at the low intensity, zero intensity, it's not that bright. At a higher intensity, you can see it goes a lot darker, the stream of light from my bulb, right? Okay, right, okay. So let's start again. So the metal over here is sodium. I've got light of a specific wavelength, which is light of a specific color that shines onto that metal, right? So I'm going to change. Oh, by the way, we also know that ultraviolet light is high energy light, right? Okay. So what we're going to do is we are going to shine. So I'm increasing the intensity to say 7%, and I shine light onto my sodium. And these little dots that you can see coming out of my sodium metal, those little dots, they represent electrons that are emitted from the surface of the metal. Right. So what do we know? When light of a specific frequency, and in this case, the wavelength of this light is 171 nanometers. And if you change that to meters, you can then also calculate what the frequency of that light is. And that specific frequency of light will emit these electrons from the surface of the metal. If I change that metal from sodium to zinc, oh, by the way, before we do that, you can see that these electrons that are emitted, they move at a certain speed between this electrode over here on the left and the electrode on the right. Now, at the moment, there is no potential difference between those two electrodes. You can see at the bottom over here on my battery or my cell over here, there is a potential difference of 0 between these two electrodes. That can be adjusted, but we'll touch on that a little bit later if we have time. So those electrons move at a certain speed between the electrode on the left and the electrode on the right. Those electrons moving in between those two. If I change it to zinc, my metal to zinc, you can see it's a little bit fewer electrons. Change it to copper. And then you can see only periodically now you have electrons being emitted. Change it to platinum. Right. And less often you'll see electrons being emitted, and they're moving at a slower speed as well. You can see that the speed that the electrons are moving, and basically what I'm trying to show you just quickly is, again, there's a difference when electrons are emitted from the surface of different metals, right? Okay. So that's a quick demonstration. So before we go to our pretest, another thing I just quickly want to show you is what difference does intensity make? Let me first show you what different colors of light make. So I'm going to go back to sodium. That is UV radiation, and those are the electrons emitted by UV light. That is the characteristics of electrons being emitted by UV light, but now UV light closer to the violet component of our continuous spectrum. And if I put it right there on violet light, that's the situation that we have. If we put it on blue light, that's the situation on green light. You can see there's quite a big difference between how frequently and how electrons are emitted, as well as the speed at which the electrons move from the left side to the right side. And if I go more to the yellow, right, I'm not seeing any electrons being emitted. Now I want to bring in the second factor. If I now use the slide control and I increase my intensity of my light, and I just quickly want to go back to, my green light. Right. So if I move my intensity right down, so you can just see a faint little bit of green light shining onto the surface of my sodium metal. You can see that very slowly electrons are emitted. If I move my intensity up to 10%, I can see my electrons are emitted more often. But what I specifically want you to notice is there a difference in the speed at which these electrons move from left to right? So just look at an individual electron, track it with your eye, and get a measure of the speed at which it is moving. So I'm going to do the slide control, and I'm going to increase my intensity. As I increase my intensity, I can see more electrons being emitted, but I don't see much of a change in the speed at which the electrons are moving. All right? Okay. Now keep an eye on that. And I'm going to move my slide control for my intensity. I'm increasing the intensity. Increasing the intensity gets me more electrons emitted, but the electrons are not moving particularly fast faster between the left side, this electrode on the left side, and the electrode on the right hand side. And I can crank up the intensity all the way up to 100%, meaning that more electrons are now emitted, but the electrons are not moving any faster than they do if there are only a few of them, right? However, and remember what I said earlier, if we change the different types of metals, we do see different speeds at which electrons are emitted. And we'll touch on that as we work through our slides. Right. I'm going to go back to our pre-test now and give you an opportunity to answer the questions for this pre-test. Right, I'm back again, learners and colleagues. There were only three of these multiple choice questions for our pre-test. Before we look at the answers, and this will also give you a little bit of context, a little bit more context. If you've chosen a specific answer, um, I'm going to have a brief discussion quickly and just add some elements for you, some more elements for you to consider. And if you want to change your answer in the meantime, after hearing us mention one or two more things, you're obviously more than welcome to do so. This first question deals with a specific graph that is given, and I always tell my grade 12s, whenever you are given the graph in any exam, whether it's a chemistry exam or physics exam, go to your axes first and see what the graph actually, the variables on the axes of your graph. So in this case, this is maximum kinetic energy of the photoelectrons on your y-axis, and then the frequency on your x-axis. Right, now remember, frequency relates to color of light. Color of light relates to wavelength, right? Remember, that's going to be our mantra for for this morning. Frequency of any specific light is related to wavelength, and that is in turn is related to color. And remember, in our when we were going through our exam guidelines, we also spoke about threshold frequency. Right, now we'll get into that after the pre-test, but just because you had to answer these questions. So there is a minimum frequency. There is a minimum frequency that will get electrons emitted from the surface of a minimum frequency of light that will be required to eject electrons from the surface of a specific metal. That minimum frequency for sodium is different from the minimum frequency for copper because the two metals are different. And since the two metals are different, you need a different minimum frequency to eject an electron from the surface of that metal. So we know that the photoelectric effect is about electrons being kicked out of the surface of a metal. The more fundamental question is this: what do we need for electrons to be kicked out? Well, those electrons need to absorb energy, right? Where do these electrons get the energy from? They get the energy from the light that shines onto their surface. Well, what is it about the light that will give the electrons energy? And the simple answer is, and I can almost hear you guys screaming the answer at me. The simple answer is light has a particle nature. There's energy packets. There's energy packets in light called photons. Remember that from grade 10? There's tiny little energy packets in light called photons. And each of these photons comes pre-packed with a specific amount of energy, right? And if the energy of that photon is more than the energy required for an electron to be emitted from the surface, or let me put it this way, if the energy of that photon is equal to the energy required for an electron to be ejected. Remember, electrons don't just jump out of the surface of a metal by themselves. They need energy to jump up. If the energy in a photon of light of a specific color is enough to eject an electron, to kick an electron out of the surface of a metal, that frequency is called the threshold frequency. In other words, the light of that specific color that has the light of that specific color, which is light of a specific frequency, shining onto the surface of that metal, if that is equal to the energy required by an electron to be ejected, that frequency is called the threshold frequency. Now, I have to say this, and I'm gonna say it twice. No, I'm gonna say it 3 times. I said it earlier. These energy packets in light, the photons, they come pre-packed. You can't pick and choose how much energy you want. The energy packets comes pre-packed. So the energy in the photon is either enough to get an electron emitted, or it is not enough. If it is if we change the frequency of light, you get energy packets of different amounts of energy. And if the energy in that energy packet, in that quantum of light, is more than the threshold frequency, there will be change left. Because remember what I said, the energy comes pre-packed. It's a specific amount of energy per photon. And if that energy is more than the threshold frequency, in other words, if that energy is more than the energy that electron requires to be emitted, my question is, what happens to the spare? What happens to the change? What happens to the extra energy? And this is where it comes in. That extra energy that is above the threshold frequency, that energy will be given to the electron as its kinetic energy. In other words, remember in the simulation, you could see electrons moving at different speeds between the electrodes. That extra energy goes in, that energy above the threshold frequency goes into the energy with which the electrons move between the left and the right hand side in my simulation. In other words, some electrons move with more speed, in other words, with more kinetic energy. And that is because the change beyond, or the amount of energy above the threshold frequency is greater, and therefore electrons move faster. If electrons are given energy by an energy packet in light, and the extra energy above the threshold frequency is a small amount, obviously those electrons will then move a little bit slower between the two electrodes. So those are the things you need to think about for 1.1. For question 1.2 relates to energy transitions of electrons. Now, electrons, remember from, I think it's also grade 10 physical sciences, when you do your Aufbau diagrams for different atoms, we learned that electrons are arranged in various energy levels. Those electrons closest to the nucleus, those electrons have the least amount of energy. Those electrons further from the nucleus, they have more energy, because pardon, the hold of the electron of the nucleus, which is positive, it is much stronger on those electrons closest to the nucleus than the attraction of the nucleus on the outer electrons. Now, electrons can move between these various energy levels, and that is what is shown in question 1.2 over here. You have n is equal to 1, quantum level 1, and so this is the energy level that is closest to the ground state. Ground state just means when electrons have the least amount of energy. And so these electrons that are higher up, those electrons are in higher energy levels. And so when electrons drop down towards their ground state, in other words, if electrons drop down from higher energy levels to lower energy levels, those electrons will emit light. And they will emit light at different frequencies. And if they emit light at different frequencies, they emit light at different colors. So that is what you need to think about for that one. And then question 1.3 is a simple question about the photoelectric effect, particle nature, wave nature of light. Right. Okay. This is just quickly before we look at the answers. It says the photoelectric effect proves that light energy is quantized, and that is exactly what I mentioned. I just didn't say it in such a fancy way. Remember, I said that light of different frequencies, it comes pre-packed with little energy packets, photons, that have specific amounts of energy. When we say that these energy packets in light have specific amounts of energy, that is what it means when we say light energy is quantized. It's just a very fancy way of saying that light energy in a quantum, in an energy packet in light, has a specific amount of energy in it. And then obviously light has a particle nature. That's talking about photons, right? Light has a wave nature. We know that light has a wave nature as well, but you must apply this question in the context of regarding the photoelectric effect. Right, let's get into it. Okay, hang on. So the answer for question 1 is B. And so that's 2. You can award yourself 2 marks there if you got that one. For 2, it is D. And for 3, it is B. It's this last one over here. Right. So when we deal with the photoelectric effect, we're specifically looking at light energy is quantized. In other words, talking about the specific amounts of energy per photon in light of different frequencies. I wish I had my pen now. I could write on this. Anyway, and then the second point, number 2, is Roman numeral 2 is light has a particle nature, and that is talking about photons. We're not dealing with the wave nature of light. Just as a point of interest, the wave nature of light is talking about light being a transverse wave, right? And so to my learners, I always make this point. We can use light in solar geysers, those black pipes that people put on their roofs to heat water, and then they store the heated water in a solar geyser. When we do that, we are not making use of the particle nature of light. We are making use of the wave nature of light, and specifically infrared, right? Infrared light is a transverse wave, right? So we're using the heating component of visible light. We're not making use of any photons. We're making use of the wave nature of light. However, when we use solar panels, also on the roofs of various homes and different buildings, when we use solar panels, we specifically making use of the particle nature of light, because it is the energy in the photons of light that is used by the photovoltaic cells as those panels. The photovoltaic cells, they change the energy in the photons of light into electricity. We're not making use of the heating component, the heat component of light. When we use solar panels for electricity, we make use of the particle nature of light. We use the wave nature of light in solar geysers when we use the heat component of light, which is your infrared light. Right. Okay, just an interesting thing to remember. Right, let's move on. Just a quick before I'll give you some more time to work on these questions. But learners will notice that this diagram that is given over here, this is a diagram of the simulation that I showed you earlier, where we have 2 controls, one for frequency. And in our simulation, our slide control was for wavelength, but it doesn't matter, because what do we know? We know that specific wavelengths relate to specific frequencies. So there's a control for wavelength or frequency, and there's a control for intensity. And this is the electromagnetic wave that is emitted onto your electrode, that's your cathode, that is made up of a specific metal. And we will know what will happen to that metal when wavelengths, when frequencies, different frequency light is shone onto that metal surface. Okay, and here we have a potential difference between these two. Between these two plates. You can play around with the simulation also to see the effect of a specific potential difference between those two plates. So a reminder that the diagram here is exactly what is happening in our simulation. Frequency you can adjust, therefore the color you can change, as well as the intensity you can adjust. And these questions 2.3 and 2.4 relates to the effect of making those changes. For question 2.5 and 2.6, you will have to go back and go and look at your equations that you were given right at the beginning. Maybe I'll just quickly go back to show you which equations I'm talking about. Right, oops, too far. Over here, we're talking about these equations over here. Right, so that is the photo. We haven't done work function discussions yet, but this is your equation for energy of a photon, which is half mv squared. This is your equation for work function, which is Planck's constant multiplied by threshold frequency, and this is your equation for the energy of a photon. Remember, the energy of a photon is equal to Planck's constant multiplied by the frequency of that light. And remember, maybe to make it fair, maybe I should have included, or we should have included the wave equation for light in here as well. And remember, the wave equation for light is c, which is the speed of light, is equal to frequency f multiplied by wavelength lambda. And speed of light is 3 times 10 to the power 18 meters per second. That's useful. That's useful information for answering question 2, the end part of question 2. So the equation is c, speed of light, is equal to frequency f multiplied by wavelength lambda. And the speed of light is a constant, equal to 3 times 10 to the power 18 meters per second. Okay, let's mark this. I hope those couple of tips that I gave you helped some of you to find your way around answering question 2.5 and 2.6. Right, okay, so I'll flip between the two screens. So 2.1, what property of light is demonstrated by the photoelectric effect? Okay, it is the particle nature of light. The photoelectric effect is proof of the particle nature of light, and that light can consist of packed, sorry, you can either say it's the particle nature of light, or that light consists of packets of energy called photons. Right. Okay, next one. Define the term threshold frequency. Now, remember, okay, let me give a couple of tips quickly as we go along, because tips always provides us with shortcuts to remembering things, isn't it? So you know that when you step through a door at a house or a building, you step through the door, you step across the threshold. That is the bottom part of your door. So threshold is that minimum amount of energy that those electrons that will be emitted from the surface of a metal. It is the minimum amount of energy required to emit electrons, right? So you can't go any lower than that. If the photon does not have enough energy, you can fire of a specific frequency of light. You can fire millions and billions of photons at that electron. If the photon does not have, if a photon in that light does not have enough energy or equal to the threshold frequency, no electrons will be emitted. Okay, so when we define threshold frequency, this would make a lot of sense. Threshold frequency is the minimum frequency, and please remember the word minimum when you write your definition. Minimum frequency of light needed to emit electrons from a certain metal surface. Right. Remember, without the word minimum, you won't get the marks for that question. Right, question 2.3. Name the visible change in the light wave with an adjustment of adjustment knob A. And if you had a look at the simulation again, you will know exactly what change is made when you change the frequency. And come, let's say it together, even if I can't hear you. Changing the frequency will change the wavelength, will change the color, right? Okay, so the color of light changes. Okay, I think by now we got that point. But we'll say it a couple of more times, and bear with me, please. Forgive me. Right. Name the visible change in the light wave with an adjustment of adjustment knob B. So adjustment knob B is the intensity, right? Adjustment knob B is the intensity one. And what did we see when we did the simulation? The brightness of the light changes. Um, bear with me, colleagues and learners, and I just want to show you what we're talking about. So on this simulation, remember, we're not changing the frequency. Well, we're not directly changing the frequency. We're changing the wavelength, but changing the wavelength because you can see wavelength is given in these numbers over here, 510 nanometers. So changing the wavelength changes obviously the frequency, and changing the frequency changes, how did we say? The color. Can you see that? Changing the frequency changes the color. And then they said, what does, so we are indirectly changing the frequency, so we're changing the color. And the second one was changing the intensity. All right, so let me do the orange one over there. What does changing the intensity do? Right, now it's just faintly orange. And can you see there? The brightness changes. The brightness changes as I change my intensity. So my answers over here make perfect sense. Changing the frequency changes the color, changing the intensity changes the brightness. Okay, let's go back. Okay. Question 2.4. Let me just move this out of the way. Name the changes in the photons with the adjustment of sorry, no, lost my cursor. Name the changes in the photons with an adjustment of your adjustment knob A. Now, remember what I said, another important thing. Light of a certain frequency will be light of a certain wavelength, will be light of a certain color. Let's add a fourth one to that. Okay, so I'm going to start again. Light of a certain frequency will be light of a certain wavelength, will be light of a certain color, will have energy packets or photons of a specific amount of energy. Right, so now we've got four things that we need to say together. So light of a certain frequency will be light of a certain wavelength, will be light of a certain color, will have light containing photons with a specific amount of energy. Remember we said that the energy is quantized in light, right? There's a specific amount of energy per photon, right? Okay. So let's keep that in mind. So name the change in the photons with an adjustment knob A. So I've kind of given you the answer there. And then with adjustment knob B. So let's quickly go through to our answers. The photon's energy increases or decreases as we change the frequency. Why? Because light of a certain frequency will be light of a certain wavelength, will be light of a certain color, will be light containing photons with specific amounts of energy. There we go. And then next one, adjustment knob B. So in other words, changing the intensity. The number of photons hitting the cathode increases or decreases. And we actually showed that in our, let me go and show you what I'm talking about. Let me show you what I'm talking about. Okay, so I am going to turn the intensity down and I'm going to give my, there we go. Okay, so electrons being emitted from the surface of my sodium metal. Look what happens to the amount of electrons being emitted when I increase my intensity. I've increased my intensity. I didn't change the color. In other words, I didn't change the wavelength and I didn't change the frequency, but I am changing the intensity. So let me turn the intensity down. Turn my intensity a little bit further down. There we go. Turn my intensity down. And I can definitely see I've got fewer electrons being emitted from the surface of my metal. All right. Okay. So that is this answer over here. All right. Okay. Let's move on. Right. To answer question 2.5, I'll just go to question 2.5 quickly so we can look at it together. The cathode, sorry, the question 2.5 isn't, it starts with this part. The cathode is illuminated by ultraviolet light with a wavelength of 330 nanometers. Electrons are emitted by the cathode. The minimum amount of energy required to release an electron is 3,5 times 10 to the power negative 19 joules. The minimum energy required to release an electron is 3,5 times 10 to the power negative 19 joules. That means that, pardon, that this is the threshold frequency. That means that this value is the threshold frequency. Why? Because it's the minimum amount of energy required to release an electron. Right. Another thing that you should look out for when you read your information, our wavelength is given in nanometers. If I want to know what the related frequency is, unfortunately, I cannot keep my wavelength in nanometers. I'm going to tell you why. I can't keep my wavelength in nanometers because I will need to use my wave equation for the speed of light, for my wave equation for light, to determine what the associated frequency for this wavelength is. And this is the problem. The speed of light is given not in nanometers, is it? What is the speed of light given in? Right, I heard you. It's given in meters per second, right? It is given in meters per second. And so therefore, it's if my wavelength here is in nanometers and I want to find out what the associated frequency is, I need to have wavelength in meters. And so then my frequency will be in the correct unit, which is hertz, right? Hertz, capital H, small z. Right, let's go to my answer now quickly. Right, so here we have our equation for the energy of the photon, right? Actually, it's the one in the middle is the equation for the energy of the photon. And what we see to the left of it is the same equation. However, instead of giving the frequency, instead of multiplying Planck's constant, which is h, instead of multiplying it by the frequency, we multiply it by the speed of light over wavelength. And that is just a rearrangement of the equation for the speed of light, which is c is equal to f times lambda. Right? Okay. And yeah, and if we rearrange everything, we come to that little setup over here. So any of these formulas, a combination of these formulas, you get a mark for that. And so what we've done is we've rearranged our equation for the energy of the photon, where we have Planck's constant, speed of light, and wavelength as my variables in that constant. And with this one, we're in the World Cup. I'm going to tell you why. Because it is so easy to find the value for lambda. Why? Because Planck's constant is a constant, h is a constant, and speed of light in a vacuum is also a constant. And therefore, it is so easy then to find the value for our unknown value using this equation. So there we go. So this is our substitution for our equation. Planck's constant is 6.63 times 10 to the power negative 34. That is the value for h in this part of my equation over here. I'm sorry, learners. I realized once I've started screening that I didn't put this save it as a PDF so that I could annotate it, so I can't write and circle and underline things as I normally would for you. But the value for h is that value over here. Then speed of light is 3 times I'm so sorry. I've been saying 18, 10 to the power 18 when I meant to say 10 to the power 8. 3 times 10 to the power 8 meters per second. That's the speed of light. And the wavelength of light was given to us in our question, which is 330. And now have a look. Remember I said earlier, we can't give it in, we can't give it in nanometer, what was it in nanometers? Let me see. Yes, we can't give it in nanometers. We must give it in meters. And that is why it is 330 times 10 to the power negative 9. So that means that this value is now in meters. That is equal to HF. And again, H is Planck's constant, 6,63 times 10 to the power negative 34, and then frequency F is my unknown, and if I rearrange my equation, I can get the value for frequency, which is 9,09 times 10 to the power 14 hertz. Right. Okay. So again, what makes it easy to answer this question is the speed of light is a constant, which is 3 times 10 to the power 8 meters per second. And Planck's constant, which is 6,63 times 10 to the power negative 34. Now, remember, both of these constants are given on your data sheet in your physical sciences exam. Your information right at the back of your question paper, both Planck's constant, h, is given to you, and the speed of light is given to you as well. Right. It is 3 times 10 to the power 8. I said 18 earlier, sorry, my mistake. And you see, even for physics teacher, and this is the other thing, advice. If ever you're writing your test or your exam, just confirm again on your data sheet. Don't be a hero. Go to your data sheet, confirm the values of each of these constants. Because sometimes when we practice these problems at home as we're preparing for exams, you use the constant values so often that you become confident that you know exactly what the number to write down. My advice to you is, even if you've practiced it and you've worked with these constants all the time, go back to your data sheet and just confirm that you have the correct value for the correct constant. Okay? And you don't write 10 to the power 18 instead of 10 to the power 8. All right, very good. Okay, let's do 2.6. The energy of the photon is equal to work function plus the maximum kinetic energy of your electron. Now, I want you to remember this one thing very quickly. We know that a photon, the energy of the photon is quantized. It's a fixed amount of energy, right? And then every specific metal has a specific amount of energy that will emit electrons from the surface of that metal. For copper and for platinum and for sodium, these will all be different values. Right. We know that once the energy is absorbed from the photon and we've satisfied that minimum energy, the threshold frequency, some energy will be left. There will be change left. There will be energy left. That energy will go into giving kinetic energy to that electron, which is the EK max part. And so if we expand our equation, we know that the energy of the photon is equal to Planck's constant multiplied by the frequency. So E there, the energy of the photon, we've expanded it here, and that is equal to the work function, which is specific for specific metals, plus the kinetic energy of your electron, right, or your EK max. So now if we put our values into our equation, our substitution into our equation, Planck's constant is 6,63 times 10 to the power negative 34, multiplied by the frequency that we've calculated up here, which is 9,09 times 10 to the power 14 hertz. That is equal to 3,5 times 10 to the power negative 19, which is the work function. Now, I'm just going to quickly go back to show you what and remind you what we, sorry, I just want to go back here. Yeah, 3.5 times 10 to the power negative 19 plus your EK max, which is your kinetic energy. And that was the question for the specific. This is what you had to calculate. So if you make the kinetic energy of your electron the subject of the equation, and you solve the value there, you get the value of 2.52 times 10 to the power negative 19 joules. All right. Okay. Okay. Learners, I will give you an opportunity now to answer question 3 for me. And again, if you have questions, please don't be shy. You will be unmuted. It's much easier if you directly pose your questions to me, and we can bounce some information off each other and hopefully get you on the right track. Okay. Good luck with this one. Apologies, the time that I've allowed for this question is a little bit shorter because there's a bit of duplication. So, and I think it should become a little bit easier for you. So let's quickly jump straight into it. Consider the following diagram of the photoelectric cell in a circuit. The values of the graphs apply to the cell. So there we have, and again, this is that same simulation, just in a different form. You have incident light onto the cathode over here, and in this case they give the frequency of the light. We know that if that the energy in the photon of that light is at least equal to the threshold frequency for the electrons to be emitted from the surface of this metal, electrons will be emitted, and those electrons will move between these two electrodes from the cathode to the anode. And we know that movement of electrons from the cathode to the anode, well, we know that movements of electrons in a circuit will give you current, right? And then there's the graph associated with that as well. And we can see that the frequency of the light indicated over here, that frequency is also given on as a value on my graph over here. Right, so let's go look at the questions. Explain why there is a reading on the ammeter when the ray of light falls on the photoelectric cell. So when this ray of light hits the cathode, the question is, why is there a reading on this ammeter over here? And you can see that the ammeter will take measurements in milliamperes. So it's tiny current that will be measured by this ammeter over here. And that is for 3 marks. So let's go to our answer quickly. When a ray of light with a frequency higher than the threshold frequency, that is so important. Ray of light with a frequency higher than the threshold frequency of the metal falls on the cathode, electrons are emitted from the metal. And I think all of you figure that out. And absorbed by the anode, which causes a potential difference, and charge begins to move through the circuit. Okay, that's a very good answer. Very good answer. So it's because of the electrons moving from the cathode to the anode that you have the potential difference, and therefore charge begins to move through the circuit, right? Then let's go back and look at question, the next one. Calculate the values for the following points on the graph. You need to calculate the value for A. So remember, A is the maximum energy of the photoelectron. So remember your equations, EK max is equal to half mv squared. Okay, so let's go and have a look at your solution. So we know that the energy of a photon is equal to work function plus EK max, or if we expand the energy of the photon to Planck's constant multiplied by frequency, that will be equal to work function plus the kinetic energy of your electrons being emitted. Substituting values into that equation as we did previously. So this is the second time we're doing a very, very identical solution. To calculate the maximum energy, you get the value of 3,07 times 10 to the power 20 joules. Right, let's go and just read the next question together. So that's for A, and let's look for B. B is, it's not, this is an energy value on the y-axis. B is a frequency value on your x-axis that you had to calculate. Right, so if we're going to look at our solution, right, now, I wish I could write on this thing. Anyway, so this equation says that work function is equal to Planck's constant multiplied by threshold frequency. Note, this is not the same as E is equal to HF. The energy of the photon is equal to HF. Work function is equal to HF subscript 0. What does that mean? It means that work function is equal to Planck's constant multiplied by the threshold frequency, where the energy of a photon is equal to Planck's constant multiplied by the frequency of the light. The big difference, tiny difference, but also a big difference. Energy of the photon is equal to Planck's constant multiplied by the frequency, which is related to the color of the light. Work function is equal to Planck's constant multiplied by threshold frequency. And that is the minimum frequency to emit an electron. Okay, so if you do our substitution into our equation, work function is 5,66 times 10 to the power negative 19, and that is equal to Planck's constant, which is 6,63 times 10 to the power negative 34. And we can therefore calculate the threshold frequency. We can calculate the threshold frequency, which is 8,454 multiplied by 10 to the power 14 hertz. Right, let's move on to the next one. Right. So how will the reading on an ammeter change if the following properties of the incident ray of light are increased? Now we've answered similar questions, but in this case we just have to give a reason, right? Only increase, decrease, or stay the same, and also give a reason. So how will the reading on the ammeter change? In other words, they're asking basically uh, for you to give a measure of the number of electrons that are emitted from the surface of the cathode. How will that change if the intensity is right? Only when we change the intensity and when we change the frequency. So here we go. Okay, ammeter reading increases. The higher the intensity of the radiation, the more electrons are released per second, and we could see that in our simulation. Increase the intensity on your, and you can play around with it also in your free time. As you increase, keep the color the same, keep the frequency the same, but play around. Take the intensity down to 0, and then you start gradually increasing it, and you will see that more electrons are released per second. And therefore, an increase in intensity will increase the current produced. Brilliant. Excellent. And then for 3.3.2, the ammeter reading remains the same. And the reason for that is the higher the frequency, the more kinetic energy is provided to the same amount of electrons. And the rate of the flow of electrons remains the same. And therefore, the current remains the same. So I'm going to go through it again. The higher the frequency, the more kinetic energy is provided to the same amount of electrons. Now, just that first sentence in your answer is so relevant, and I want you to write this down Actually, I want everyone listening to me to write this down. In the higher frequency, if we change to a higher frequency, it means that more kinetic energy will be given to your electrons being emitted from your cathode. But it is more kinetic energy, meaning they move faster. But it is the same number of electrons being emitted that just move faster. In other words, it's changing the intensity that changes the number of electrons per second. But changing the frequency keeps the number of electrons per second the same, but those electrons just move with more kinetic energy, but it's still the same number of electrons. And if you still have the same number of electrons, that is not going to change the current. So the speed at which these electrons are released from the cathode, that doesn't change the current. It is the number of electrons that is released from the cathode per second. That changes the current because it changes the rate of flow of charge, which current is. Remember the physics part of it, electricity? Current is a measure of the rate of flow of charge. And so this is a very, very important distinction about the effect of changing the intensity and changing the frequency in the specific experiment. And I think most of you listening to me now notice that that specific simulation is key to understanding the whole, well, a large percentage of the photoelectric effect. Right, brilliant, brilliant, brilliant. Okay, question 4, I'm going to give you an opportunity to answer this, and then we'll touch base shortly. And again, here's our experiment again. And I think you guys can see, if you can understand the simulation, you're in the game. Right, good luck with this one. Okay, right. Again, it's a lot of similarities between this question and previous ones. So we're going to jump straight in and have a go at answering these questions. Again, it's excellent advice that Mr. Mentor gave about you guys going and have a look at the simulation and play around with it. This is actually quite fun. Before we answer the specific question, just a couple of things, and I just want to repeat again some strategies that we use, some tips that you will have to remember, well, at least between now and just after you've written your physics paper 1 grade 12s. Try to remember some of these tips. When we tackle these questions, we have to know what our equations are. And so those equations are given on our information sheet, our data sheet at the end of the question paper. We have to familiarize ourselves with the quantities for the constants that we use, that is the speed of light and Planck's constant. We also have to be careful that any values for wavelength that is given to us other than meters must be converted to meters. We also need to be very familiar with what not familiar, know off by heart all of our definitions for work function. Work function talks about energy. Remember, work function is energy, and that's why the symbol is W. W, energy. Work function is the minimum energy required to, and I'm just saying it quickly, you're going to use the definitions as they are in the exam guidelines, but is the minimum energy required to emit an electron from the surface of a metal. And then threshold frequency and work function, they go together. It's because threshold frequency is also minimum, but not minimum energy, but minimum frequency required to emit an electron from the surface of a metal. So work function, W, talks about minimum energy. Frequency, that's F subscript 0. That refers to minimum frequency. So just keep that in mind. Okay, let's look at question 4. A group of learners investigates the photoelectric effect. They set up the photoelectric cell and measured the maximum kinetic energy of the released photoelectrons from the metal X using different frequencies of incident beam. So the only difference between this one and the previous question is the following. It's the same setup, but in the previous question, the frequency of the incident light was fixed. It was fixed. In this one, it says that we change the frequency. We use different frequencies of incident light. And what do we know? Changing the frequency will change the wavelength, will change the color, will change the amount, the number of energy per photon. Okay, remember 4 things that you have to remember. Changing the frequency changes the wavelength, changes the color, changes the amount of energy per photon in that specific frequency. Right, okay. So question 4.1, define the term photoelectric effect. And by now, this is exactly the way you stated. It is the process whereby electrons are ejected from a surface or a metal surface. Now, you'll see that these are underlined. So the examiner specifically wants this phrase in your answer. Electrons are ejected from the surface when light of a suitable frequency is incident on that surface. Right. Basically, it's just a fancy way of saying when we shine light of a specific frequency onto that metal surface, then electrons will be ejected from it. Okay. Right, let's go back and look at our question for 4.2. For the above investigation, name the independent variable. So a simple way, and we've said it throughout your studies of physics, the independent variable is the variable that you change. Right, and remember the difference between this setup and the previous question was, in the previous one, the frequency was fixed. And in this one, the frequency, it says we're using different frequencies. So it's no surprise then that our independent variable is the frequency. Now, can you see? They don't only say frequency, they also say wavelength, and they also say color of incident light, because those things go together. Right. Oh, brilliant. Okay, let's go back again. Sorry. Right, 4.3. When ultraviolet light with a wavelength of 272 nanometers. Right. What did we say? Since the speed of light is in meters per second, wavelengths that we deal with must be in meters. So that is immediately, if while you're writing your exam, you kind of make a note, you can even underline it. My frequency is in nanometers. Don't forget to change it to meters. Is shown on on metal X. The kinetic energy of the released electrons is 1,56 times 10 to the power negative 20 joules. Right. Identify metal X using your table below. Right, now in this table, they give you various metals, sodium, calcium, potassium, and zinc, and they also give you the threshold frequency for each of these metals. Remember, the threshold frequency is always the minimum frequency, where work function is the minimum energy. Right, so here they give threshold frequencies in hertz, and these are the various values over there. Obviously, we will have to do a calculation to identify metal X, and whatever our answer is, we will need to find a corresponding answer there. So let's go and look at our solution for that, and here it is. If we use our equation for the energy of the photon. Okay, so I'm going to take a slight step back from the solution that is given over here. I'm first going to say that the energy of the photon, because this is how we've done it the whole morning, so we're not going to go and change it now. Energy of the photon, this is E over here, is equal to work function first. Work function is W subscript 0 plus Ek max. That's how we start. So now we can expand it. The energy of the photon, therefore, is equal to Planck's constant h multiplied by the threshold frequency. Why? Because h multiplied by the threshold frequency is work function, right? Plus Ek max. Now we can expand the energy of the photon bit again. Energy of the photon, and let me take another quick detour. Before I go from here to here, I will first say that the energy of the photon is equal to hf. In other words, Planck's constant multiplied by frequency. If I expand frequency, frequency is equal to speed of light c over lambda. So now the energy of the photon becomes hc, Planck's constant multiplied by the speed of light over wavelength. And that is equal to Planck's constant multiplied by the threshold frequency, that's the work function part over there, plus Ek max. And if I now do my substitution into my equation, I can calculate that threshold frequency over there because the kinetic energy of the electron was given to us. If I make threshold frequency the subject of my equation, I get to 1,08 times 10 to the power of 15 hertz. And if I go to my table, I will see that this threshold frequency is equal to the threshold frequency of zinc. Now, learners and colleagues, I just want to reiterate this as well. This is obviously not the only way to do this calculation. And I know that some of your educators, you may have taught your learners to first calculate the work function value over there. And then from there, if you know what the work function is, use that equation for work function to calculate the various components of this. This representation that you have over here is just a quick and easy way where you do all of your calculations in one go. Okay. Right, let's move on to the next question. Oh, sorry, the next question was 4.4. Apologies. There we go. 4.5, sorry. The ultraviolet light is now replaced with a bright blue light, and the ammeter in the circuit still shows a reading. So we've changed the color of the light. In other words, we've changed the frequency, we've changed the wavelength. How will the kinetic energy of the released electrons be affected by the change in the incident light? We've changed the incident light and choose increase, decrease, or stay the same, and also explain your answer. Right. Okay. Did I miss? I think I missed the question. I missed the question. The Ek max was the 4.4 bit. Apologies, colleagues and learners. I'm just going to go back to question 4.4. I think I've missed 4.4 over here. 4.4, calculate the speed at which, so we've identified metal X. Calculate the speed at which the electron are released by metal X. That's the part that I forgot. That's 4.4, right? Ek max is equal to half mv squared. So we know what the maximum kinetic energy of my electron is. That is 1,56 times 10 to the power negative 20 joules, and that is equal to half mv squared. Now this may initially seem like a tricky question because you're going to think, but hang on, nowhere in the given information is there anything about the mass of an electron. Okay, I want you to just take a quick pause over here with me and grade 12 learners. So this is a type of question where you go back and you think, oh, flip, I need to calculate a velocity, which is v. And in my equation, fine, maximum kinetic energy, I've got that. I've got V as my unknown, but I've also got M, and nowhere in my given information am I given any. Let's go back and go see. Nowhere in my question over here is there any mention of the mass of an electron. And so this is why it's important to keep your eye very, very focused on that data sheet, information sheet at the back of the question paper, or the data table at the back of your question paper, because the mass of the electron will be given to you there. You're not required to know it out of your head. And that is where we get this value from over here, 9,11 times 10 to the power negative 31. That's in kilograms. That's tiny. Multiplied by v squared. So if you make v squared, if you make velocity the subject of your equation, you then calculate the speed of the electron to be 184,960,88 meters per second, right? Which is very fast. Okay, so my tip for the solution here is when you are asked to calculate a question like this, where, say, for example, the velocity of an electron, remember you will need the mass of an electron, and the mass of the electron will be given to you on your data sheet. This is 9,11 times 10 to the power negative 31. So congratulations to all of those learners that could do this calculation and that could identify that even though the mass of the electron is not given in the question, that you must be alert and say, aha, but I can go and find it. I may not remember out of my head what the mass of an electron is, but I can go and find it on my data sheet, that value over there. Right. Okay. And now finally we got to 4.5. The blue light has a lower, the answer is decrease. The blue light has a lower frequency than the UV light. The kinetic energy will therefore also be less or decrease, because the kinetic energy is directly proportional to the frequency of the incident light. That is a very, very important statement right at the end of this answer over here. The kinetic energy is directly proportional to the frequency of the incident light. You may want to jot that down as well, or maybe underline it if you've written it down as the answer. And what does it mean? It means that as your frequency increases, your kinetic energy will also increase. That's of your incident light. Because remember, as the frequency of the incident light increases on a, let me put it like this. Hang on. Let me put it like this. Your metal stays fixed. So make your metal your fixed variable. So say we have zinc as our metal. So I'm not going to change the metal, but I am going to change the color of the light. When I change the color of the light, I change the frequency of the light. Now, remember, zinc has a specific work function. In other words, there's a specific amount of energy required to emit an electron from the surface. And when the incident light, whatever the frequency of the incident light is, meets the threshold frequency, anything above that will go into, or any change that is left goes into giving the electrons energy. And the more change there is, the higher above the threshold frequency of that specific metal you are, the more energy will be available for the electrons in the form of kinetic energy. And therefore, the faster the electrons will move. And therefore, we can comfortably say that the kinetic energy of an electron is directly proportional to the frequency of the incident light. So when we talk about the incident light, we are talking about the color of light that changes, that falls onto your cathode. Okay, brilliant. Okay, here's our post test. We're doing really, really well this morning. We've got about 7 minutes left. This is our post test. Have a go at answering these questions, and then we'll give some feedback in 3 minutes or so, maybe, yeah, make it 3-4 minutes. Right. 5.1, the line emission spectrum is formed when electrons in the ground state moves. Okay, so you can see the options that are given over there, and your answer is B for that one. And electrons in a higher energy state moves to a lower energy state or the ground state. I mentioned this right at the beginning. That is when you have your different quantum levels, N3, N2, N1. N1 being the lower energy state, and so that is what that refers to, right? 5.2, the sodium cathode of a photocell is irradiated with ultraviolet light as shown in the diagram below. The ammeter registers a current, and again, this is exactly the same setup as we had in the simulation. Which one of the following changes will increase the ammeter reading? And your answer for question number 2 is B, and increase the intensity of the ultraviolet light. Now, remember what we said. It is when we increase the intensity, we increase the number of electrons emitted per second. And increasing, and so the rate of change will make a change in the rate the rate of increase of electrons being released will directly affect the current, as current is the rate of flow of charge, right? Okay, 5.3, light of a certain frequency is shone onto metal M and electrons are ejected from the surface. The same source of light is shone onto another metal N. So you first had metal M and now you have another metal N. The electrons ejected from the surface of metal N have much higher kinetic energy. Now we can make a very important conclusion from that. If the electrons in metal M have a higher kinetic energy, it means that the threshold frequency of metal N is lower. Why? Because all the energy above the threshold frequency goes into giving the electrons kinetic energy. I'm going to say that quick. I'm just going to say that one more time. If we change from metal M to metal N, and the electrons emitted by metal N has more kinetic energy, it means that metal N has a lower threshold frequency. And how do we know that? Because all energy of a photon above the threshold frequency goes towards the kinetic energy of those electrons. Okay. So if you look at our answer for question 5.3, your answer is D. And reading it there, it says the threshold frequency, I think we've said it a few times, of metal N is lower than that of metal M. Right. And I think that is the end of our session. Beautifully, we've ended at just before 10.